to take their seat. Welcome to this inaugural lecture this evening. It's my honor to present Professor Daniel. Well, he was there for a second. So yeah, that's me. No! Okay, this doesn't start well. That's me. To welcome everyone to this inaugural lecture. This is always a special occasion. It comes with becoming a professor, although Daniel just told me that he has been a professor since 2023 already, so we can already call him professor, but it is an important part of this process and occasion to celebrate. Daniel is originally from Melbourne in Australia, and he came to the UK as a student in Cambridge, and then to Imperial College in 2005. I think originally as a PPARC, or STF. PPARC was the STFC in the days, yeah? A fellow, and then 2011 as an academic. And now in 2023, he has become a professor. Daniel is working on statistical problems in astrophysics. He has worked on Planck and other projects. And he will talk to us about statistical problems today. And normally, in such an occasion, you wouldn't talk about religious affiliations, but I have been told he's a Bayesian. So we'll learn more about this. Let's start.
Well, thank you very much for that introduction, and thank you all for coming out on a very cold night. And yes, you'll be hearing about Bayesian things and statistics and astronomy. My position here at Imperial is somewhat unusual in that I'm half in the maths department and half in physics, and that's why I've got the challenging task tonight of talking simultaneously about these two topics here that I've highlighted in red, astrophysics and statistics. They may not seem like natural bedfellows, but actually their history goes way back centuries, and we'll see today as well, they're sort of embedded together as sort of an embodiment of big data and big science. But I'm going to start close enough to the start. So for those of you who wondered what color my hair was when it had a color, it was a sort of fairly nondescript brown, so sort of no major loss there. This is me on my 13th birthday, and you can already see the tools of the trade here for, it's a little bit small, but I'll count Doctor Who as representing sort of astrophysics and space. This thing in the middle here was an amazing combination of ruler and slide rule and triangles and draftsman tool called a Mathomat that was a pride of place in my high school kit as I was growing up. I've also got a mild interest in cricket, as you can see here from this cricket trivia book. But why I thought Garfield was funny is now something that I no longer understand, so those have all gone in the recycling. But actually, my interest in space started before that when I was even at kindergarten. I got a book, something like this, which, as you can see, sort of shows the majesty of the solar system in this case. It also shows sort of a childhood personality disorder and a current job description. So very handy there. So this book went in and out of the library every 4 weeks. I would go and re-borrow it and pore over these pictures. Unfortunately, the example I found here, the version of Saturn is bordering on the grotesque, because really my first obsession was the fact that this stunning object existed in the natural world. It still kind of seems unbelievable to me that something so amazing should exist. However, it had competition, of course. So Saturn is amazing with its rings. But as a child who was also interested, maybe a bit too interested in numbers, I was insanely bothered by the fact that Jupiter was larger. So this was a major source of sort of dissatisfaction for me. And I'd sort of try and open up the book in the hope that this time Saturn would be the king of the planets. And you mentioned religion before, so this also sort of had an interaction with that. One time I went for a play date with a friend called Ben from kindergarten, whose parents, little to my knowledge, were Dutch reformist ministers. And for the first time in my life, grace was said before we had lunch, and I was asked to renounce Satan. And I said, well, but Saturn's my favorite. And this obviously didn't go down too well. And so then the riposte was, well, do you love God? And I said, no, I love Mum. So that was a sort of an early indication of where my philosophical leanings were going to lie. So I wasn't invited over to Ben's house again after that. But I did actually run into him about 20 years later, and I told this story, I thought, in the vein of strange things parents do, at which point he revealed that he also had become a Dutch reformist minister. So that ends the story with Ben. So that was already, astronomy and numbers were starting to come together here. And there was also another source of numbers in my childhood that we can see here, with apologies to Stanley Kubrick. So this, I'm guessing most people in this room know that this is a cricket ball, and enough people in this room will know that I'm pretty enthusiastic about cricket. And because it's Christmas, we have to have a trivia quiz. So this is a screen grab of the equivalent of the BBC in Australia, the Australian Broadcasting Corporation. So this is their homepage with the contact details. And you can see here that the post office box, if you want to send them a letter, is 9,994. So anyone care to guess why they have chosen that number for their post box? Don Bradman's batting average. So this is an extremely important statistic. So this is the first introduction of statistics into the talk here. It is something you can calculate from data. It's very simple. It's just an average I'll describe in a second. And of course, marks him out as a truly astounding cricketer and possibly the most dominant sportsman in history. Less dominant is me. And I don't average 99.94. So this is a sort of gentle introduction to the sort of data analysis problems that, well, it's not an astronomy one, but it's one that I like, and did a sort of calculation for I think it was a student assignment about this. So yeah, for those of you particularly who don't know cricket, the game is, this part of it at least, is very simple. Batters try and score runs, they get dismissed, and the average is the number of runs they score between dismissals. So it's a very simple statistic, just a straight average. But the tricky thing is that sometimes the batter's innings is ended not because they're out and they've failed, but because the match is over or the innings is over or something like that. So they have a bunch of incomplete innings in amongst their completed ones for which the average would be very natural. This comes up also in sort of life expectancy calculations. So you get the sort of thing you're trying to estimate life expectancy, and you have to deal with this tricky aspect of the data that for people who have died, you know how long they lived. But for people who are still alive, all you know is that they at least will live to their current age. So it's exactly the same problem, but obviously this is more important. If you look here, so these are some quotes, admittedly not from the most exacting sources, but there seems to be this sort of law, and I've had this from cricketing friends as well, that if you have lots of not-outs, that inflates your average, because you get to score some runs in those innings, but they don't contribute to the bottom line of the fraction, and that somehow by being not out a lot, that means actually that your average is an overrepresentation, with the equivalent of saying, oh, these people who are alive are sort of skewing the numbers somehow. So there are lots of sort of invented approaches for how to do this, but I think there's one clear answer to problems like this, which is the one that Stefan mentioned, which is that you take a walk 1 hour, 50 minutes sort of east-northeast of here. So we are down here in the Blackett Laboratory, and over there in East London is the tomb of Thomas Bayes. So you can go and visit this, and I did that last weekend. So that is me, and that big stone thing with all the moss on it is where the Reverend Thomas Bayes lies. And he is sort of, well, in some sense, a one-hit wonder. He did one significant thing in his life, but I would say that it... But actually, I think that's the way forward. But the editors at Cambridge University Press demand that it's this way. But anyway, so this equation is my entry, if there was such a competition, for the most important equation in science. It embodies the scientific method in that it's a way that you incorporate data, always keeping track of your uncertainties, and it allows you to analyze everything from cricket averages to cosmic microwave background radiation, or what I'll talk about later with quasars. And there's two simple parts to it. In fact, I can simplify it. It's really only the top part of the equation that seriously matters. And this is the only part of this talk that I consider something important that I'm saying. Everything else I hope is interesting, but this is important. And in this case here, all these p's are probabilities. And in every case, it's the probability given whatever you're assuming on the right-hand side, how much that implies whatever it is on the left-hand side that you're considering. And if you define probabilities like that, you have sort of near infinite flexibility about what you can reason about. And in particular, the reason that Stefan mentioned of this as being a religion is there is another sect called frequentism, where you associate probabilities with how often something happens as opposed to how well evidenced it is that it's true. So that's one important thing. And the second then is this structure on the bottom here, where there's two parts to every calculation. Everyone agrees that there's a relationship between how well, say, the model predicts the data. That will definitely be part of the evidence for whatever you believe. But the important thing here is that there are always assumptions that underlie all data analysis problems that you do. And the nice thing about this, and one of the most important things I guess I emphasized to students this morning and you today, is that it forces you to write down your assumptions. And if something is wrong with them, then that's the sort of place to investigate. So you can do that for the cricket problem. Like I said, I did this for a problem sheet, but one of my countrymen, Brendan Brewer, who's now a sort of quite prominent statistician in New Zealand, actually wrote a paper about this and did all the hard work of modeling the process of batting and analyzing the real data of real cricketers, and found what the reason it's called getting your eye in is this idea that when you go out onto a cricket field and have to try and hit the cricket ball, initially it's quite hard, or it's always quite hard in my experience, but it does get a bit easier after you've hit a few balls and scored a few runs. So that's this trend here that you start off very vulnerable to getting out, and then as you get your eye in, even 10, 20 runs is enough, your sort of ability to score high increases. So what this means is that if you look at this question about how not-outs affect averages, that this law that they inflate averages is actually flipped. That because of the fact if you have a short innings that's curtailed because the game ends or it rains or something, that actually means you've done the hard part, or at least some of it, and been robbed of the chance to cash in. So the reason I mention this, or one of the reasons, is that it's very personal to me, because if you look at this is an example of big data. If you look at this column here, so these are from 2 of my cricket clubs, some members of which have been kind enough to come along tonight. This column here, the vertical one, is the number of not-out innings. And you can see there that basically because I'm not very good at it, I get to bat quite late in the game, and so end up with these little funny innings and get curtailed, and I get not out again. And so actually people say, oh, that average, it's a bit high, it probably should be lower. But we have the evidence now that that's not the truth. So yes, this is an example here. Obviously, I have a love of numbers and data. This is an example from cricket, but the original big data subject was and is astronomy. So I show this here for 2 reasons. This is Tycho Brahe. These tabulated data here are these carefully curated measurements that then, with Johannes Kepler's work interpreting and modeling them after Brahe's death, is the reason that we found out that the planets orbit the sun in ellipses. So the starting point of this was careful data collection and then Kepler's careful analysis. Of course, I also wanted to show this because actually until I Googled today, I had no idea about his extraordinary moustache, which is something that I'll work on. So this is the start of astronomy as a data science, a slightly strange phrase that I'm guessing most of you have heard at some stage, which to me seems almost like a truism, as in if it involves, science necessarily involves data, so you don't need to call it data science. A later example here is Henrietta Swan Leavitt. So these are her tables now from early in the 20th century. And again, what sort of marks this to me is the sort of absolute respect for the preciousness of measurements, empirical measurements of the natural world, tabulating them carefully. And they mightn't seem exciting as a table of numbers, but they're the reason that we found out there are pulsing stars called Cepheids, where you can predict their pulsations and will enable a later plot, basically, that Hubble's discovery of the expanding universe is based on this work here of an underappreciated astronomer. An astronomer who has got, I would say, considerably more appreciation is Vera Rubin. I hadn't seen this photo before. It's a lovely shot of her just engrossed in the night sky, presumably looking at Saturn. She has the most remarkable, well, maybe not the most remarkable scientific project, I'd say the most remarkable astronomy project named after her, which is the Vera C. Rubin telescope. For those of you who know, it'll do the large synoptic survey of space and time, LSST, and the logo of this here, so on the left-hand side here, you see what are obviously stars and planets, unfortunately none of them with rings, and then the flow here is partly because it scans the sky in an arc like this, but the output here is data. So this is a central part to the working of this survey. It's something that turns the night sky into data that we can process, or actually maybe not, because the data volumes are so extraordinary, it's not 100% clear how well we'll be able to do with this data set. And so much so on their website, doesn't matter if you can't read this, but this highlighted here is saying that that's explicitly why that is part of their logo. So it's going to be an extraordinary data set. It's also an extraordinary device or scientific piece of equipment. Here is a picture of me and my partner standing in front of it. It actually is real. This is in Chile at an altitude of about 4,000 meters. The building itself from the outside is quite amazing. This is jaw-dropping. So this is the telescope itself with a mirror that is almost as wide, not quite as wide as this room, that can tilt and slew across the sky at incredible rates, and this fantastic piece of engineering that obviously, you have to be an astronomer to get in. It's not like a tourist site, but I did the hard work and became one. So this was an absolutely joyous day. So on the right there, you see me and my parents looking sort of probably the proudest and happiest I've ever saw them. And then also, this is with my supervisor, Rachel Webster. Obviously, they each took the photo of each other. So this was way back in 2000. You can see I've got my proud certificate, which for a while I thought I'd lost. And because I had the silly hat on, there were other mere graduates who wanted to have photos taken with me, which I thought, yeah, big celebrity, that's very exciting. And it wasn't until I sort of shook their hand and said farewell to them that I saw I was holding the certificate upside down. So that was sort of, doing a PhD was, the start of being able to work on astronomy, as I thought. At the time, even though the word statistics appeared in my, or statistical appeared in my thesis title, at that stage, for instance, I'd had a physicist statistics education, which is to say essentially none. And when I saw a statistical problem, I did what physicists think they can do, which is if it involves numbers, I'll work it out for myself. And so some of it was okay, but some of it was pretty poor. And it's only later, really, when coming to Cambridge, that I got sort of connected with people who were really applying cutting-edge statistics to astrophysics problems, and that was the sort of the touchstone that really has driven all the rest of my career till now. So this sort of newspaper clipping here is a bunch of paper titles of mine. None of them are statistics papers. They're all astrophysics or astronomy papers. And the highlighted words are a whole bunch of different topics within astronomy. And I am not remotely an expert in all those topics. I'd say, if anything, I'm maybe an expert in one. But the reason I've been able to work in these different areas is simply because if you can do statistical data analysis, you can get involved in just about any area of science that you want. One of my guests here, David Hand, is very fond of saying that the best thing about being a statistician in science is that if something moves on or something's exciting, then you can go and join that and play a part in whatever those things are. We saw that 5 years ago when some of my colleagues, not me, used their statistics skills to model COVID interventions and so forth. So they were able to sort of pivot and suddenly do what the world needed from them. So obviously I'm going to spend 10 minutes on each of these topics. We'll go through to midnight. No, I'm going to pick out one topic which has sort of gone through my research career since my PhD, which was largely about quasars. So in fact, this catchy little title here, Binary Quasars, was my first ever paper, and my most recent one is this one here with an automated method for finding the most distant quasars. So this is the sort of the substantive topic I've chosen to sort of focus in on a bit more detail. And of course, the first thing I need to do before getting anywhere with that is to define what a quasar is, because I'm guessing plenty of people in the room don't know. So this is not a quasar. This is something that I've probably rivals Saturn for its sort of sheer glory. It's what's called a grand design spiral galaxy, sort of like what the Milky Way would look like if you could leave it and look sort of down on it or up from below. It's a vast collection of hundreds of billions of stars, all orbiting. You can see that sort of spiral pattern there. And right at the center, see that? Maybe, maybe not. So right at the center, that tiny little black dot there, I guess I can point at it, is a supermassive black hole that has a mass of something like maybe between 1 billion and 10 billion solar masses, which is obviously an extraordinary object, and you might think that would be something that dominates the galaxy, but in fact, that little black dot there is overscale by a factor of 1,000. So what it really should look like when I do that transition is just that. You can't see it, and yet we have a 1 billion solar mass black hole sitting there at the center of the galaxy. And we all know black holes look like this. As I'm guessing most of you know, that's a publicity image from the film Interstellar. And actually on that same trip where we saw the Rubin Observatory, we ran into people who did special effects work on this film. And I confessed that I didn't actually really like the film very much, even though I thought it looked very good and I liked the physics. And the response was, oh, well, you need a degree in physics to understand it. So obviously the next few minutes were quite joyous as I read through my CV. But actually you don't need a degree in physics to know that if you go into a black hole, you don't come out in your daughter's bookcase. So this object here is their simulation of a black hole. The black part is obviously the black hole proper, and this glowing stuff is material around it, just in a disk, a bit like rings of Saturn, but the light coming off it is deflected by the black hole, so you see this sort of halo, and that bit at the top is really the backside of the disk behind the black hole. And there was a lot of fuss about this. I'm guessing there's some people in this room who sort of saw headlines like, Hollywood film influences science, major science result papers came out written by Nobel Prize winner Kip Thorne about others, about the calculations here to actually see how the light behaves in the vicinity of the black hole. And I was quite sure that I'd seen this before, and indeed I had. So this, yes, it's not Hollywood level special effects, it looks more like Doctor Who, but it is a picture from a paper from appropriately named Luminae in 1979. So he had done exactly the same calculations with obviously far inferior computers and without Matthew McConaughey, but this was a known thing. So I was a bit annoyed that Hollywood sort of got the credit for doing this the first time. So this is the point of this, though, is that's what a black hole looks like, or is simulated to look like. And then this is the real version. So this, admittedly, as a graphical image, it's not the most astounding thing. But when you know what it is, then I think it sort of stands up for itself. So this is the actual image of that glowing material around the event horizon of a black hole. In this case, the black hole at the center of a nearby galaxy called Messier 87, and it has a mass of about 5 billion solar masses. So the black hole is obviously in the middle of the donut, and there's this glowing ring around it. And the reason I'm focusing on this material around the black hole is that's what a quasar is. So a quasar is the material falling into one of these supermassive black holes, and in fact the reason that it grows and gets to that mass is that it's fed by gas and stars that have been torn apart. And because of the extreme physics, it glows so brightly that it outshines an entire galaxy's worth of stars. So if that grand design spiral had had a black hole, a quasar in the middle of it, then actually all the telescope would see would be the light from that central object. Not that I'm obsessed by the solar system, but it's a good reference point here. So we're back to our home turf. So this is our solar system with the sun in the middle, and obviously not quite to scale. But to sort of get a reference for what a quasar is like physically, if I took the sun and replaced it with a black hole where the event horizon was about the radius of the sun, and then replaced the entire disk of the solar system with white hot gas that was emitting X-rays, and then gradually when the gas gets to the middle of this interior region here, plunging into the black hole, that's what a quasar is. So it's a truly remarkable object. And we can see that if we look at them visually, because it's quite obvious which of these astronomical objects is a quasar, right? There's one that completely stands out. So no, there is not. If it wasn't for the little crosshairs, you wouldn't know that all the other objects other than the one that I've just highlighted there are ordinary stars in our galaxy, fairly close to us in sort of cosmological terms, that are amazing objects in their own right, but not exactly newsworthy. Whereas that one dot that I've highlighted there is 3C273, the very first quasar that was discovered, and initially was called quasar as a quasi-stellar object because no one had the slightest clue what it was, other than that it wasn't a star. So we have this slightly strange thing that I'm saying. There's this amazing object that we can see into the distant universe because they're so bright. We have ordinary stars, and they look identical in the way that I think most people see astronomy done, that you look at the sky visually or look at a picture of it and you identify things from how they appear. But you can't do that here. There's no way you could identify that object from all these other ones. So it's Pink Floyd to the rescue. And the fact here that the light from all these objects, if you put it through a prism or similar optical device, you can split it up into the colors. And it's not just the colors of the rainbow here, even though one of them's missing for graphical reasons. But of course, if I was to look beyond the red here, then I would get into the infrared at longer wavelengths. And as I looked beyond the purple here, I would get into the ultraviolet, short wavelengths, very high energy light. So all of the electromagnetic spectrum is accessible if you can spread out the light from an object in terms of wavelength rather than looking at its shape. So because we're going to have a look at a couple of diagrams like this, this here is an example. The top is what you'd actually see if you had a high-pressure sodium lamp, split up the light in a prism, and actually looked with your eyes. You'd see this, again, this sort of lovely sort of rainbow color, a bit like the Netflix logo, and that's how it would appear. But the way a scientist, in sort of researchers represents this is sort of bin the light and make this plot here which shows how much light is being emitted at each different wavelength. It's a bit like a probability distribution. So you see for these sodium lamps here, there's not much light in the blue and the violet. There's a lot in the yellow and the orange. And you can do that not just at the wavelength that the human eye can see, but all the way into the infrared, ultraviolet, radio, X-ray, gamma rays, etc. And this is actually how we do most of sort of the scientific astronomy of working out what's going on in an astrophysical object. It's not, in most cases, the way it appears on the sky. It's the way it's the fingerprint of the spectrum of the light it emits. And the nice thing about quasars, actually maybe it's not a nice thing. A thing about quasars is that they have very distinctive spectra. So if we focus on this blue curve here, so this is just a plot of wavelength, the same as before, sort of colors from the ultraviolet to the optical, and then through into the near infrared. You can see here that this blue spectrum has got this sort of smooth, decreasing emission with wavelength, increasing wavelength, and then these giant emission lines that it turns out you can associate with different atomic species. I'm not going to go into the detail of those, but the important thing is that if we have a quasar here, this one is well, relatively old, seen when the universe was only 2 billion years of age compared to the 13.7 that it is now. And this one in red down here is one seen as it was in the early universe. And this harks back to those paper titles where the sort of the big thing we were doing here is hunting for quasars in the early universe, basically the first quasars. And there's three differences between the blue and the red here. The big one is, I guess, that the red is at a lower level. That's just because it's further away, and so it appears less bright to us. Nothing too exciting in that, the inverse square law. The second thing is that these features here, these emission lines, appear, they're all the same emission lines in the same order and the same ratio of wavelengths, but everything is stretched. And that's because of the cosmological redshift, the sort of universe's equivalent of the Doppler effect. So we see things that are further away, then we see all the wavelengths stretched out, and what might be emitted in the ultraviolet, we might see in the infrared. And the third thing that will come up importantly as well is that you'll notice there's this part of the spectrum, there's a dashed line here, which in the blue spectrum we see for real, and for this one in the early universe is missing. And that's because of a third effect, which is that in the early universe there's neutral hydrogen, which has subsequently all been ionized and separated out into electrons and protons, and that absorbs all that light at shorter wavelengths than this emission line. So we have a sort of signature of what quasars look like if we can get a spectrum, and what ones in the early universe look like if we can get a spectrum, and particularly that they're invisible to the naked eye, essentially. And so I mentioned there's this redshifting effect. This is simultaneously one of the most important and one of the most awful scientific plots ever made. So it explains, though, why this redshifting effect is so important, this cosmological Doppler effect. So this is Hubble's famous plot showing the distance to a bunch of comparatively nearby galaxies on the horizontal axis and their velocity away from Earth on the vertical axis here. And the important thing here is that the two quantities are correlated. And what that corresponds to is the idea that if things that are further away are moving away from us and moving away from us by more, that's the universal expansion. That was the demonstration just under 100 years ago that the universe is expanding and not static. But if I was marking this, if you were one of my students, and I think there are some students that I see here who are maybe doing their final assignments, so take note. The vertical axis is in the wrong units. It's got units of distance rather than velocity. There's no error bars on these data points, and also the fitting method was dubious as well, and it turns out in the end he had the slope wrong by a factor of 10. But the important thing was there was a slope. So that means that if you can see these objects where they're at sort of very high Doppler shifts, or red shifts as we call them, then we know that we're seeing them far away because of the fact that distance and this redshift are correlated with each other. And then even more importantly, it's not that we're interested in seeing what the universe looked like over there, because we believe it looks pretty much the same as here. What we want to do is see how the universe looked back then. And of course, if you're seeing something far away, you're seeing it as it was in the past because of the time the light takes to travel to us. So what's annoying for science fiction fans, because you can't have galactic empires, because you can't communicate and organize yourself, is fantastic for astronomy. Astronomy almost wouldn't work as a discipline if we couldn't look back into the past and see the early universe like this. So the group of people, all Imperial based at one time or another, sort of working at this. There's a bunch of faces there that some of you might know. It was Steve Warren, who I came to start working with here on this project in 2005. And then there's a bunch of people there who have been either postdocs or students here. The ones who are currently here, William Martin, who's a PhD student of mine, and Arv Hughes, who's working on this project now as a postdoc, and is almost recognizable with the microphone. You'll see him later, although that was back in calmer hair days. So we want to find these quasars in the early universe. And what we have to do is we don't have these spectra. To take a spectrum of an astronomical object is time-consuming and resource intense, costs thousands of pounds to do each one, and you basically can't get enough time on telescopes to take spectra of more than a few interesting objects. So what we do have is back to working with images of the night sky, but as we saw with that example of the first quasar discovered, images aren't desperately useful for identifying these things. There's a second problem, which is these quasars in the early universe, these very first supermassive black holes are extremely rare. Over the whole night sky, we're talking sort of in the hundreds. And unfortunately, other astronomical objects are anything but rare. So what this is like an image from an atlas of the entire night sky spread out. And all I'm going to do is zoom in into these rectangles each time. And further in, further in, further in, and further in. So this final image here is basically 1 pixel on that initial image, and there are something like 10,000 stars just in that tiny little area. And we're looking for sort of hundreds of objects over the entire night sky. We can't get spectra of all of them. If it were, then I'd be out of a job because you wouldn't need any statistical expertise. So the question is, how are we going to do this? And the one thing that you can probably see here is that all these objects, which are almost all stars in our galaxy, look identical in terms of their shape. Maybe the one here that looks slightly different, that's only because it's bright enough that it has these diffraction spikes from the telescope. They're all just dots. But they are slightly different colors. So that means, in principle, we can separate these objects because we know that the things we're looking for are very red because of the fact that that effect of the early universe absorption in the redshift means they don't appear in the optical and they do appear in the infrared. So that's one way that we can get at these objects. And on the right-hand side here, you can see that if you had another red object, a brown dwarf, a very cool star that's red because it's basically like sort of glowing coals, it sort of doesn't emit very high temperature radiation. If I had this spectrum here, if I had this curve, and I had this sort of target for a quasar, then, well, a bit like reviewing Interstellar, you don't even need a science degree to be able to tell that these two things are different. That's trivially to identify. But if I was to obscure that and only give you this image or this image on the left, then that's a more challenging problem because, well, they're both little red dots, and the question is one a good candidate quasar, or is one of these much more numerous brown dwarfs that are interesting in their own right, but not what we're looking for? We're sort of dominated by this contaminating population. And so the answer to this is, not the answer to this. So the nature of this problem is that we've got two things that to us look almost identical, one of which is maybe 100 light years away, and one of which is maybe 10 billion light years away. So it's the equivalent of not being able to tell whether something is a mark on the window or a crater on the moon. That's the sort of level of the difference in distances. And this was illustrated by this Channel 4 documentary, which I'm just going to show a short clip of.
Okay, one last time. These are small, but the ones out there are far away. Small, far away. Forget it.
So, okay, poor Father Dougal wasn't doing very well there at trying to tell the difference. But the difference in the size and the distance between the toy cows and the real ones was maybe a factor of 100 at most. We're talking about an embarrassing failure on the order of sort of a factor of billion in distance. So what's the resolution to this? How do we solve the problem? There's one way. So Bayes' theorem here becomes the best way to do what essentially is a classification problem. I've got a bunch of data, a bunch of these images of these stars where all I've got is sort of basically measurements of their colors, and I want to classify them into false positives, things we're not interested in, and target quasars that are worth spending the time on the telescope to get a spectrum to confirm. And there are lots of different ways to, there's paper after paper every day on classification problems. But if you're in the lucky situation that, in this case here, your prior is essentially, can you model these two populations, the sort of demographics of the properties of these objects, and here we can, and you know the way in which the telescope imperfectly records how bright these objects are, because there's always measurement noise in just about any physics measurement, and including this one here. They're the two parts of this equation. And we have that for both our contaminants and our targets, and we put those together through Bayes' theorem, and that gives us a probability for every single object being either what we're looking for or something that we should discard. And so, yeah, this was our innovation here of tackling this problem afresh and using, I can't say modern statistical methods, but perhaps optimal statistical methods. And what it turned out that it was sort of 10 times more efficient than any previous approach that had been adopted. So when we had access to this data and were looking for these objects, we had one problem was simply finding them at all, and a second problem was finding them before the other people who were looking through the same data for the same objects. And long story short, we won. So this is the constellation Leo, and this is what happens if you could zoom into Leo, and we're sort of going to go through a sequence of images from different astronomical surveys that are sort of deeper and deeper every time. They sort of replace each other. And I apologize, it would have been nice to have Pink Floyd playing here, but unfortunately they broke up. So the New Age music you're going to have to put up with. And you can see that as we zoom into this constellation, slightly longer than I think, but eventually, out of all these, so these are all just stars in our galaxy that, yes, they're no doubt very important to the alien civilizations that live around them, but to us are just annoyances. And then finally we get in here, and, well, to the limit that the lights will allow us to see, that little object there. So you can imagine now how hard this is to find in this cosmic haystack is, well, it's gone past there, that little red dot, but you saw that, I trust, at the end. So that little red dot on the sky looks like nothing special, but when you take a spectrum of it, that's not a spectrum. When you take a spectrum of it, I'll show in a second, we can confirm that, first of all, it's a quasar, not a star, and secondly, by the wavelengths at which those sort of prominent emission features appear, we can confirm that actually it's a quasar in the early universe. And this, at the time, was a big leap forward back towards the Big Bang, and it was the first, the earliest supermassive black hole that we'd found, and caused even more trouble for the existing theories of how these objects formed. So, of course, seeking the glory that comes with science, we published this, or got it published in Nature. That's not actually a member of a team with a sample from the object, but we did sort of get onto the cover, albeit in sort of very small writing. And also we made, got a bit of newspaper coverage, which was very nice too, including in the local section of the Hawaii Herald Tribune, which I thought was a very open-minded approach. So this is the spectrum that I mentioned before. So this is, hopefully, even if you hadn't seen quasar spectra before, you sort of recognize that this looks similar to those sort of representative spectra I showed you earlier. So it's exactly what we were looking for. There's all this absorption. So this quasar is emitting very strongly at these wavelengths. And because it's in the early universe, none of that light gets to us. And then these broad emission lines here are from the material orbiting very close to the supermassive black hole. And so what we'd found here was a 2 billion solar mass black hole seen as it was 770 million years after the Big Bang. And since then, the field has moved on. We've sort of, other people have discovered similar objects further back towards the Big Bang, earlier, further away. And there is this huge, you could call it a debate, but I think it's more just general puzzlement. No one can work out how these objects formed. So that's one of the big questions in extragalactic astronomy. And it will hopefully be answered, or at least progress will be made by the Euclid satellite. As a childhood science fiction fan who, I guess, I've got time to briefly mention that I actually saw Star Wars in the cinema on first release, sat between my parents who weren't sure whether taking a 3-year-old to see Star Wars was quite the way forward. We went in and there was the music and the spaceships and all the rest of it. And then at one point, Mum sort of nudged me and said, "Are you okay?" And I said, "Shut up." Because I was hooked. So this is not an elegant spaceship like the ones from Star Wars, but it is one that will progress this area of science and is, well, that's what it looks like for real. I'm always terrified seeing things like this. You can see just a person there to give you a sense of the scale, with these high fashion hairnet. Terrified of seeing these things where it just looks like it's about to fall over. And that sometimes happens when people forget to put in the bolts, but you'll notice that's a different satellite. That didn't happen to Euclid, and it went past all its manufacturing tests. And we see it here sitting on top of Falcon Heavy rocket run by SpaceX. And then this happened. No, fortunately not. Fortunately, Euclid sitting on the same launch vehicle, but about 8 years later. That was a 200 million pound satellite, by the way, that went up in that one. But this is the real version.
3, 2, 1. Ignition. Liftoff. Visual propulsion is nominal. Vehicle is pitching downrange.
So you can imagine how terrifying it was watching this, but you can see there it's cleared the scariest part, it's cleared the launch tower, and in fact made it all the way into space. And we're not going to track all of its flight, but it's now sitting out at L2 and taking beautiful data. And I'm going to finish basically with showing you the first release of data from Euclid's survey. So this again is the night sky, a bit like I showed before, but now more obviously in an ellipse. So the New Age music, yes. So dearly beloved, we are gathered here today. It sounds a bit like Prince. So this is the night sky as we see it. And then the area that Euclid will survey is this orange area. So notice it's dodging our galaxy because our galaxy is too dusty and filled with stars to survey very effectively. And then this is 10% of Euclid's survey. And we can see we can sort of zoom in here. And the basic thing that this satellite does is take images of the same quality as the Hubble Space Telescope, but whereas Hubble was only able to look at tiny little areas of sky, Euclid will survey roughly a third of the sky at the quality that the Hubble Space Telescope was able to only for very small areas, basically bespoke special objects that were of interest. So I don't actually have anything to say over this other than, again, just how beautiful our universe is and the fact that I guess I think it's worth spending this money and time and effort to actually see, the world that we live in. Not so much money and effort was spent on the soundtrack. So that's zooming into the most remarkable and interesting and beautiful objects in the survey. And now, if we pull back out, you see just how much detail he is when we go to the full scale. And now the jigsaw piece goes back in. And Euclid will cover 1/3 of the sky, basically all of the sky outside the parts that are looking into our Milky Way. And we will search that for these most distant quasars and, of course, a whole lot of other exciting science. There is the team that's doing it, with me 3rd from the left and Arv, 8th from the left there, outside a fantastic building in Heidelberg, which if you look down on it is shaped like a spiral galaxy. You can see the end of one of the arms. So we're already getting first results from this. There are sort of discoveries that have happened that are embargoed, nothing record-breaking or anything like that, but the data is of the quality that we're hoping for, and so the idea now is that we find out more fascinating things about the universe, probably. So thank you very much.
Thanks, Daniel, for this inspirational talk. We'll have the opportunity to ask questions. No questions on cricket, please.
Them I can answer.
And we'll have questions both from online and from the room, but Let's start with the room. And if you have a question, please wait for the microphone to reach you. There's one in the back.
Hello, that was a wonderful inaugural lecture, and I'm very pleased to hear it. The graphics in that final video were beautiful. You know, they're sort of, they tear your heart out in the beauty of them.
Absolutely.
But how much of that information is within the visual spectrum, and how much is purely due to various other radiation that we receive?
So I didn't talk too much about this, but actually I can go back to showing this spectrum here of these representative quasars eventually. There we go. So, so as I said, to give the reference here, the sort of objects that we're looking for are like this one that's shown in red, where they're essentially invisible at wavelengths shorter than 1 micron and visible at wavelengths longer than 1 micron. And that roughly demarcates between the optical, which the definition of optical in astronomy is a bit vague, but roughly corresponds to what our eyes can see, which is between about, on this scale, between about 0.3 and 0.7 microns. And yes, so we expect the target objects we're looking for to be invisible in the optical and visible in the near infrared. And Euclid has got 4 different filters that it looks through, each of which, because it's making an image, looks at a sort of broad range of wavelengths. There's one that is in the visible, which covers sort of this wavelength range here. And one of the key things that we will key off is that for an object to be of interest to us, it has to not be visible in the optical. But then it's got 3 other filters which cover this range here from sort of about just over 1 to around 2 microns. So between them, you've got 4 filters there, 3 in the infrared, or the near infrared, and 1 in the optical. And so what they do to make those beautiful images is that it's a sort of a fake RGB image where they use the infrared as the red color there. And I don't know exactly which combination of filters they are, but the visual gives you the sharpest images, and then the difference between how bright an object is in the infrared and the optical gives you the color, where it sits, whether it appears blue, young stars, young galaxy, or whether it appears red and old and colder. So I hope that answers your question.
There's a question here.
Thanks for a lovely talk, Daniel.
This is not fair, no colleagues.
I just would like to know what your method for finding the probability of an object being a quasar. What does it actually produce? So what are the probabilities that come out? Are you looking at a map of the whole sky with probabilities assigned to it? Or?
So if we go to, say, an image like this here, so this is sort of an effective zoom in. So of course, yeah, what we would like to have is data of the sort that we see on the right, and then we don't need probabilities or anything much at all. It's obvious what's. And so the catalogs, that idea of these modern observatories taking the sky and turning it into a table of numbers, is that for every single object that we can detect, you systematically go through the sky and find all the things that stand out as a detectable source. And then for each of them, you have, for Euclid, basically 4 measurements, how bright it is in each of the 4 filters. And you have an error bar on each of those. And you have a giant table of billions of objects where you have that entry for every single one. And then you simply loop over that object after object and compare whether that data for that particular object is more probable for one of the quasars that we're looking for, or more probable given that it's one of the contaminants we're trying to avoid. You do that, calculate a marginal likelihood, to use the technical term, compare them, and the output is a single number that is not only between 0 and 1, but is a probability, and then it's up to us to have a threshold of how far down that list we go.
And what was the threshold for the quasar that you found? What's the number?
So we had a threshold of 0.1 because in all these sorts of things where you've got different choices of models and sort of models, statistical models for the noise, there's always this question of, well, how accurately am I really getting those distributions? So you have sort of adopt a conservative level. And in some ways you would say, why don't I just go down to a half? If it's less than a half, it's probably not what I'm looking for, but we wanted to be more inclusive because we didn't fully trust our models. But there's a plot I was very proud of in one of our papers where we showed that actually all the objects, so we checked down to 0.1 to be really conservative, sort of an engineering approach, but all the objects that were the targets that we were looking for were above 0.9.
Thank you.
Are there any further questions? Anything online? Yeah, Alan?
Yes, there's two. One is a fairly short one from Paul Keenan. Has your batting average improved, Professor?
No, I could show you a plot of my batting average as a function of time, and it looks rather like this quasar spectrum here. Unfortunately, a few highlights, but it's been rather plunging. But I'm working on updating the software that does the averages to incorporate the effect of knot-outs properly, so that should help.
Okay, and the science one.
That was science.
Yeah, okay. Coming from Aditya Apiraj, who's in the sixth form. How do Bayesian methods account for uncertainties in observational data when identifying quasars in big data?
Okay, so that's an excellent question. So if we come along and imagine, I hope you can see the cursor online, I'm pointing at sort of that particular red dot there. So most of the objects that we're looking at are not really bright things that stand out like stars in the night sky. There are always more fainter objects than bright ones, and so in any astronomy survey, most of the objects that you can see are sort of at the faint end of things and are more like objects that it's definitely there, but it's clearly not a very precise measurement that you're going to get of that. And so one of the important things about the method that we came up with for selecting these objects is that you could imagine having two objects where they've both got exactly the same colors, they're exactly the red color that you expect, and you don't see anything at the optical wavelengths. But imagine one was, say, 5 times as bright as the other, and so your relative error bars were 5 times smaller. For the bright one, you had a really precise measurement of these colors, and for the fainter one, your best guess for the color of the object is the same, but it's got much bigger error bars. And so the traditional methods would simply not take any account of the error bars at all. They would simply class these objects by the measured value, and you put them in or out of a selection. For us, we say, okay, we're going to calculate these probabilities that incorporate those error bars, and one of the nice features is that those two objects potentially will be classified differently. So the one that has got small error bars and a precise measurement, if it's consistent with what we're looking for, will get a big tick and a high probability. And the other one with the larger error bars will get a much lower probability because there's much more chance that it's one of the contaminants that just by coincidence has ended up looking a bit like what we're after. And you can see the extreme version of this. If you imagine turning up the error bars to bigger and bigger levels, so worse and worse data, eventually you'd get to the stage where there's no difference between having massive error bars and not having made a measurement at all. And so in that case there, your result correctly comes back to the ratio of the numbers of the two objects because you haven't learned anything from the low quality observation. So the error bars are very important.
I think that's what we try to teach all students.
I do.
Error bars are very important. Statistical analysis is at the core of so many things. It's really fascinating. Are there any more questions in the room? Yeah, please wait for the microphone. Who has, oh, sorry, there's one up there.
You said 3C237 was the first quasar discovered. When was it actually discovered and how did it get its name?
It's a very exciting name. If you have children, don't call them 3C273, unless you've had 272 children first. So yes, so this rather unprepoposing little dot in the sky here. So 3C stands for the C stands for Cambridge. The 3 stands for third because it was first detected in the third Cambridge radio survey. So this was the Nobel Prize-winning work of Martin Ryle in Cambridge in the early 60s. So they did a sequence of radio surveys of the sky, the first time really this had been done. This object was detected in the third of those surveys, and you'll be astonished to discover that it was the 273rd object catalogued. So the name is just purely bookkeeping. And so because it wasn't a special object, it was just yet another source that had been found. The way it was discovered was that it was special. Was the first thing that happened was the spectrum was taken of it, I think, just as a standard part of having all these radio objects, taking spectrum with an optical telescope just to see what they were. And they found that this object had a very high, for that stage, redshift, even though it was a tiny little point source that meant it was brighter than a galaxy if you took its redshift to indicate its distance, but that it was not extended. It didn't look like one of those big spiral galaxies. So it was some tiny thing that was out producing the radiation of an entire galaxy. But the problem was that, before that, there's a really cool thing. Before they could find the object to take a spectrum of, the radio location of this was very poor. So the radio data said, to a good approximation, it was roughly somewhere in this image. You couldn't even tell which of the optical sort of star-like objects it was. And so they had this fantastic idea that they found, it turned out this object was going to be in the path of the moon. And so what they did was waited for the moon to go across this object and block it. And then if you're observing in the radio, you don't get the position accurately, but you get the time that it suddenly switches off very precisely. And so you know you can see it, you can see it, you can see it, and then at that instant you can't see it because the moon's in the way blocking the radiation. And so you know that this object must be on the line defined by the edge of the moon, and that got you the location. So I think that was a wonderful way to do science.
Where's the microphone? Oh, there.
It'll come to you.
So you've mentioned the instruments on Euclid that you're using to help you find quasars. Mm-hmm. I was wondering if there are instruments on other telescopes, such as James Webb, perhaps, that you have or are hoping to use to find quasars?
James Webb is, of course, really the headline-grabbing, recently launched space telescope, which, much as I like the Euclid images, the images it's produced are something, again, and the science that's coming from it is unbelievable. The big difference is that James Webb is like Hubble. It's capable of producing extremely high-quality images, but of only very small areas of sky. And so it is finding high redshift objects, but much less luminous ones. So rather than these very bright quasars, which are sort of material flowing into a billion solar mass black hole, it's capable of finding the more numerous, fainter ones. So it's certainly contributing to this. For what we're aiming to do, the problem is it'll never do a big enough area because we only have 100 of these objects dotted across the sky. James Webb, I'm not quite sure what the field of view is, but it's sort of much smaller than a big crater on the moon as you see it. So it's I would say it's complementary. And what James Webb has done specifically in this question of how the first supermassive black holes formed is that it's found these earlier objects, so earlier than these bright objects we've found, with black holes at lower masses. And so there's a sense of trying to it's a cosmological game of join the dots. We think that those objects that we're seeing there are the precursors of these ones with the larger black holes that we see later. But trying to piece that evolution together is currently one of the big open problems in astrophysics.
Okay, perhaps one more question and then we should move on.
Yeah, you don't miss out this time.
Yeah.
A bit of an overall question, but can statistics prove the theory of the multiverse or more than one universe existing?
So I guess there's two parts to answer this question. One of the important things that I would say differentiates not just statistics, but sort of scientific data analysis from, say, pure maths, is that basically proofs are never going to come because everything that we say about the universe is contingent on some sort of observation or data, eventually all of which have got some sort of level of uncertainty. So even bedrock theories like gravity or evolution or something, are contingent. There's always the possibility that we're wrong about them, and science has the possibility to roll that back. So it certainly won't be proving anything. The trick with the multiverse question, so multiverse can mean two things, but I'm guessing you mean the version of this where every time a quantum measurement is made or a choice is made, that we have two different copies of us, etc. Yeah. So the problem with that there is that it's, on the one hand, a very beautiful theory that completely resolves all the philosophical troubles with quantum mechanics about the sort of collapse of the wave function and when something's measured and not, because it's simply measured in our universe to be this way and in another one of the multiverse universes that way. But to the versions of the theory that I'm aware of have got this sort of safety device that says we can never observe those universes. So it's not just that statistics can't prove it, is that the theories themselves say if this thing exists, it's completely inaccessible to us. So it has that sense of, not that it's not a reasonable theory to think about, but the idea if a scientific theory has to be disprovable, the multiverse theories don't tend to have that property. But I personally think the disprovable requirement is, it's an important idea, but that doesn't mean it's not worth thinking about. And who knows? If that were the answer, it's not its fault that it can't be disproved.
Okay, we should probably thank Daniel again. And in this universe, we actually move now to the vote of thanks. I have to admit that being new to Imperial myself, I don't really know what a vote of thanks is, so I'm really excited to see this for the first time.
Well, thank you. I'm not sure I do, actually. I'm enormously flattered to be asked and said to Daniel on multiple occasions, "Are you absolutely sure?" And he kept saying yes. It's clearly got nothing to do with distinction or competence, but I have known him a long time. I think probably longer than anybody in this room, unless they're actually related. Yeah. So I thought I'd just tell you a few things about how he started off and indeed first came to the UK, because of course many of you are very familiar with him in the present day. So I'll go back to 1982. He was only 10, 3 years younger than the photo we saw rather beautifully with the book collection. And I ended up in Cambridge, having finished my degree in Edinburgh. And I found a second-year research student, PhD student from Australia, Rachel Webster, who was kind of looking for something interesting to do for her thesis. And we hit it off, and we spent the next 3 years working on her thesis, which duly appeared and was awarded. And then she went via some time in Canada, back to her homeland, and took up a position at the University of Melbourne in 1992. And at that time, Daniel was, I guess, halfway through your undergraduate area. So he was doing a 4-year master's degree, which he successfully completed in 1994. And in fact, he was too modest to say to you, I only showed you the graduation picture, but he came right at the top of the class. And he'd persuaded Rachel that it would be a good idea to take him on as a PhD student. And he started in 1995. I think that's right. Yeah. And Rachel and I were still working with each other. And at that time, finding gravitationally lensed objects where you're looking out into the distant universe and seeing objects that are basically gravitationally impacted by massive things lying between us and the objects were really becoming possible, and you could do statistical surveys. And that was, in fact, what we were concentrating on at that time. And in fact, there was a large international astronomy symposium held in Melbourne in 1995. And in fact, what Daniel said about his first paper isn't quite true. I think that was probably your first refereed paper. But there's a 2-page summary of what you were planning to do for your thesis, pretty much, that appears in the complete record of that conference, which I was fortunate enough to attend. But had to return, of course, from the couple of weeks we spent in Melbourne to Cambridge. And then after another couple of years, I was never clear whether Rachel just needed a break or she thought I had to put up with him, so now it's his turn. But the University of Melbourne came up with a postgraduate travel study award, and you appeared in Cambridge for 6 months in, I think, 1997 was when. And he had the misfortune of having to put up with me for that time. Went back, and I told the main feature from the perspective of Melbourne was, in fact, the lack of his input into cricket and indeed several other sporting areas, including football. And even when he was with us for that short period of time, he was busy working quite hard, inducing interest from our students and indeed postdoctoral researchers into cricket, surprisingly. So he finished the thesis, I guess, in 1999. Is that right? That's right. And again, he was too modest to say, but the University of Melbourne has Chancellor's Awards. There are two of them, one for the humanities and social sciences and the other for kind of STEM subjects. And there's one for each PhD, the best PhD produced in the university each year. And Daniel was indeed the recipient of the Chancellor's Award for the STEM subject. So he was quite good. And it turned out that I hadn't put him off Cambridge completely. So when he was exploring post-doctoral places to land, he decided both to have a subject change and move from gravitational lensing to the cosmic microwave background and come to us in Cambridge, where you spent 6 years. I think that's... and so he became a key member of the group that took on the Planck data analysis. And he went through a very effective period. He was way more productive than when he was working with me. Lots of citations and lots of papers. And so if you look back, he was definitely contributing to the Institute's profile. On the other hand, there was also a downside, which came about because of the cricket and the football. Now, in modern parlance, it would come under the well-being head. And he was busy inducing the postgraduate students and the postdocs to actually start playing regularly cricket and football and the like. And they duly did, and they were all very happy. But it was, well, I don't know whether dangerous is quite the right way to say, but I mean, before Daniel had really got people playing cricket and football, you know, once or twice a year you'd encounter a student, you know, somewhere in the corridor with a crutch wandering along, because they'd had a cycling accident. But after Daniel had got the students playing football and cricket, the number of people you encountered coming down the corridor with a crutch and, you know, a leg in a complete, you know, sort of things how it couldn't move. It was normally legs, although occasionally it was arms, increased by about a factor of 10. And you say, what happened? Oh, well, I had to stop the ball going in the net, but Richard fell on me or something. Or Sophie hit the ball very hard and I've got to get better at catching for the cricket. And the funny thing was they weren't at all fazed. They'd actually just wanted to know how rapidly it was they could get back to playing again. So he really induced the entire place to go for the Australian sporting approach. I mean, I think Addenbrookes A&E basically had a separate queue for, oh, it's this week's, you know, astronomer from the sport. So, but on balance, I think he was still a good thing for our output. And then he mentioned, in the kind introduction, you acquired a distinguished long-term fellowship and you pinched him, essentially. You moved here, I guess, after 6 years with us, as you say, for 5. I then started working with him again, actually. So he gained a lot of the Bayes expertise with the cosmic microwave background work, but then started on things far away. If I looked it up on the NASA ski, I think we produced 38 papers together. I know some of them are not refereed. And also the thing he didn't tell you is that the first 2-page summary of what he was going to do in his thesis has acquired 3 citations since 1996. 2 of them are self-citations. So it didn't make an enormous impact. But on the other hand, the Redshift 7 paper, rather more recently, we have improved, and that's rapidly heading to, I think, towards 1,400. citations. So we have got better working together since then, and I'm very lucky. So now I think you brought home how you've managed to combine completely different subject areas given your statistical approach and analysis so successfully. And I'm now looking forward to what you will be able to do, as you said, with the Rubin LSST and the Euclid satellite going forward, and also contributing both to the student body and indeed the researchers and faculty at Imperial in the future. So thank you for the lecture. Thank you very much.
So thank you very much. Thank everyone for coming. I think there will be occasion for a drink outside, and thanks for this outstanding lecture. And the proceedings are closed. Professor?